Hello, my friend. Today I'm going to present a video on Minfield game, and our case study is 60. I will talk about the application of the Minfield game in 60. And as you can see, the title is an overview of Minfield game, a 6G case study. My name is Yusuf, and I'm going to present this video. Here you see the outline. We start with the main idea, an example of a school of fish. Proceed with how are things in Minfield game theory. We introduce Hamilton-Jacobian and Fokker-Planck equation and the interplay between them. We talk about Minfield game assumption, their application in 6G network. We discuss about the idea of the Minfield multi-agent reinforcement learning. We present Minfield hybrid proximal policy optimization, and finally we summarize everything in Minfield representation of the UAV, which are integral parts of the 6G network. And finally we present the reference. Okay, what is the main idea? As you can see here, in classical game theory, each agent interacts individually with every other agent. Let me repeat. Each agent interacts individually with every other agent. This will result in a huge overhead in the network. Okay, when we have more than two or three agents, a classical game theory faced with curse of dimensionality, and they are not a good option for managing a large number of the agents. Classical game theory just work for a small and limited number of the agents. Okay, but what happened in Minfield game? In midfield game, each agent interact with the mass of others. Okay, each agent interact with the global behavior of the other agent. As you can understand, in midfield game, each agent don't individually interact with other agent. Just the agent interact with the global behavior of the other agent. This reduce the number of interaction and communication overhead and make the problem realistic. In scenario when we have a very large number of the player, when we have infinite number of the player, we cannot interact with each of them individually. We need to characterize the behavior of the global and just react to the behavior of the global. This is the main idea of the Minfield game. Okay, let me introduce you to the example of the school of fish. Imagine a school of fish. In classical game theory, every fish reacts to the action of the nearby fish. Okay, every fish react to the other fish individually. This is very complicated due to the vast number of interaction among the different fish. Okay, we have a school of fish with infinite number of the fish, and every fish is reacting to the other fish individually. This results in a huge overhead. Okay, uh, and in this case we need to use midfield game. Each fish need to just to characterize the global behavior and just respond to this characterization. Okay, okay, how are the things in midfield game theory? As I discussed in the previous slide, in midfield game theory, each fish doesn't care about each of the other fish. Each fish doesn't react individually to the other fish. Rather, It cares about how the fish nearby and the mass globally move. In simple language, each fish characterizes the global behavior of the other fish and just respond to this characterization. Okay? Each fish react only to the mass, to the global behavior. Okay? This is the main idea of the Minfield game. Okay, what is Hamilton-Jacobian-Bellman equation and Fokker-Planck-Kolmogorov? Please carefully look in this figure. We try to convey to you the idea of the Hamilton-Jacobian equation. You can see we have a school of fish here. Each fish is represented here individually. Each fish has a imagination of the global behavior. This fish has a imagination. This fish has imagination, and the same for other fish. Okay, the reaction of this individual fish to this global behavior of the other fish is characterized with Hamilton-Jacobian equation. Actually, we derive Hamilton-Jacobian equation based on Bellman equation, and then by solving it, we can obtain or control or action and respond to the mass, to the global. Okay, this is the main idea of the Hamilton-Jacobian. But what is Fokker-Planck equation? Fokker-Planck equation govern the moving and change in this school of the fish, how the global behavior change. When we solve Fokker-Planck equation, we obtain mean field, which give us the average behavior of the other. Okay, actually, in simple language, this Fokker-Planck tell us how the behavior of the school of fish change over time. Okay, how this behavior change over time, and what is the rate of the change in the school of the fish. Okay, this is the main idea of the Fokker-Planck equation. Fokker-Planck equation characterize the global behavior of the school of the fish and how this global behavior change over time. Okay, in this figure, you see the interplay of Fokker-Planck and Hamilton-Jacobian. As you can see, we solve the Fokker-Planck-Kolmogorov equation and obtain the mean field, which is the average behavior of the mass. We obtain the mean field after receiving the mean field using the Hamilton-Jacobian equation. We derive or control, and this is a loop and is repeated over time. The Millfield game theory is the interplay between Fokker-Planck equation and Hamilton-Jacobi-Bellman equation. Okay, we solve the Fokker-Planck equation, obtain the mean field, then based on the mean field, we drive our action and react to the global behavior. Okay, what are mean field game assumption? The first assumption, infinite population. I think this is clear. We have an infinite number of the player, or we have a very large number of the player. We have rationality assumption. Agents are assumed to be rational, meaning they optimize their individual utility function based on their available information and the anticipated aggregated behavior of the population. We obtain this aggregate behavior of the population, as I discussed it, by solving the Fokker-Planck equation. Okay, and a rational agent just optimizes its utility. And third assumption is homogeneity. Agents are considered to be homogeneous or interchangeable. This means that the identity of any individual agent doesn't matter. The identity of Any individual agent doesn't matter. Only the aggregate behavior of the population is relevant. What is matter for us is the aggregate behavior that we characterize using Fokker-Planck equation and solve it to obtain the mean field. Then agent use Hamilton-Jacobian equation to derive its action to react to this aggregate behavior. Okay, mean field game nowadays is very common in 6G network. It can address a scheduling problem, routing problem, dynamic task planning, energy efficiency, caching control, interference control, velocity control, power control, resource management, trajectory design, and security. Later in this video, I provide an example of trajectory design and velocity control using unmanned aerial vehicle. Okay, now what is the main idea of mean field multi-agent reinforcement learning? Let me please forget this slide and carefully listen to me. Imagine we have 100 agents, okay? Each agent to obtain its Q value needs to compute the joint action, okay? But we have 100 agents, and obtaining the joint action is not practical. Obtaining the joint action is not practical. So we have the scalability issue when we have a large number of the player, when we have a large number of agents, because we cannot characterize the joint action. Okay, what is the solution? How we can make multi-agent reinforcement learning scalable? Okay, the idea is that each agent should compute its mean field based on information receiving from the neighbor and use that mean field, here you see characterized as OI, as input to the agent uh, to compute its Q value. When we use the mean field, when we use the information from neighbor to characterize the mean field and provide it as input to the agent, we make the system actually scalable, because in this case we don't need to characterize the joint action. Okay, we just compute the mean field and pass it to the agent to compute the Q value, and this idea replace the computing of the joint action. This is the main idea of the mean field multi-agent reinforcement learning. Actually, mean field idea make the multi-agent reinforcement learning scalable, and any agent is independently able to compute its Q value and don't need to compute the joint action. Okay, here you see mean field hybrid proximal policy optimization. That is part of my PhD thesis. I provide the relevant reference in the last slide. In this work, we have computed the mean field based on the information from neighbor and provided it as input to the agent plus to the state. And so the agent independently compute the Q value. We don't compute the joint action. We have infinite number of the player, and we don't need to compute the joint action. We compute the mean field, provide it as an input to agent, and independently compute the Q value. Actually, what we did a decomposition. We decompose the system, and each agent is independently compute the mean field and then compute the Q value. Okay, mean field representation of the UAV. Look, please. if we want, the objective here, we want to optimize the velocity based on the state information, that is the trajectory or location of the UAV. If we want to use classical game theory, each this UAV have to react to this one separately, react to this one separately, react to this one separately, react to this one separately. This is not possible in the presence of the infinite number of the player. It imposes a lot of overhead. That's why we have to use the mean field game idea. In this way, this uh, UAV characterize the global behavior of this UAV using the Fokker-Planck equation, solve the associated Fokker-Planck equation, obtain the mean field, and then UAV just react and respond to the mean field. Okay, the game is played between the UAV and its mean field. The same story is true about other UAV. Finally, we reach to the equilibrium. Okay, here you see the reference. This is the main paper of the mean field multi-agent reinforcement learning. This is the paper of my PhD thesis, Age of Information Minimization using multi-agent UAV based on AI enhanced mean field resource allocation. You can find good information about mean field game in this paper, and also this is a recently published paper by the team of Professor Juhan. This is a good reference, a good and valuable reference on 6G application in UAV network, and the example of the school of fish is derived from the last reference. Okay, thank you very much uh, for watching this video. If you learn something from this video, I appreciate to like and subscribe. Thank you very much.